Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, so it is my extraordinary pleasure to introduce Dave Levin, who will soon be getting his PhD from the University of Maryland. Dave is so prolific that a single advisor couldn't keep up with him, so he's being jointly advised by Bobby Bhattacharjee and Arvind Srinivasan and Neil Spring. He's interviewing for a position with either the Networking Research Group or the Distributed Systems Research Group. He has interned with us twice, and one of those internships resulted in a Best Paper Award from NSDI. In addition to NSDI, Dave has published in SIGCOMM, Infocom, Sigmetrics, IPTPS, and NetEcon multiple times in most of those venues. He's also a Live Labs Fellow. And for the past few years, he's been taking economic theory and applying it to real deployed collaborative systems to address a fundamental problem. And that is that as these systems get larger and larger, the people whose machines and devices are involved in the systems tend to know each other less and less. And that results in a situation where the success of a system is dependent upon collaboration among a bunch of people who have no reason to trust each other and strong motivation to act selfishly. So there's really two ways to react to that. You can say, well, it sounds pretty hopeless, or sounds like a challenging research problem. So you can judge for yourselves which way Dave reacted.
Thanks very much for the introduction, JD. I'm really excited to be here, and I'm excited to present some of this work to you because I feel that it represents some of the techniques that are going to be involved in the designing of systems for the future of the internet. So before we get into the future, I'd like to start a little bit with the past. So this is my very abridged sort of metro map of the history of the internet, of systems design. So I think you can kind of decompose it along two axes. First are how many users were there, and what could we assume about the users? So very early on, there were very few users, and we could assume that they were altruistic. We're all in this together. The internet was this technological playground where we just wanted to see if we could get this interconnection of computers. So the first question was, can we build it? And the answer, of course, was the resounding yes. They built it in 6 days, and on the 7th day, that's a different story. But in any case, they did build it, and they saw that it was good. And just like all good things, it then more people became interested in it, and many more users. Many people started becoming interested, and people actually with competing interests became interested. But the big question here was, can we scale? Can we scale these networks? Can we scale these systems that we're building? And one of the major insights into solving this problem, which of course the answer is yes, can we make it scale? Of course we can. One of the major insights there is as the demand grows, as participants join the network and start demanding from the network, you also have them supply back to the network. So this is sort of the fundamental insight behind peer-to-peer systems, for example. So now we have this, at this point, this turning point where very early on in the internet, sure, it was designed to handle attacks, but the assumption was that the attacks were going to come from outside of the network, from tanks and mortar strikes and trying to bring down the network. And now, as we start trying to make the users also part of the infrastructure, we have this notion where now the attacks are going to start coming from inside of the network. And these attacks can come sort of two broad ways. And so we start seeing that no longer can we assume that everybody's going to be altruistic, but rather we might have malicious attacks, those who would attempt to bring down the network, say for fame, notoriety, or profit. And one of the questions there is, can we protect the network from inside, from those acting maliciously from within? And then finally brings us to this last stop in our metro map of the internet, which is these selfish users, those who try to gain from the system, who don't necessarily try to bring it down, but want to gain as much as possible with incurring as little cost to them, say in terms of energy, in terms of monetary costs, or in terms of the contributions of bandwidth they have to make to the system. Can we provide incentives? So what this means, I look at this, I think back on this history, and what I think one of the main sort of turning points and the thing that drives my research is this observation that network systems now must account for the competing interests of stakeholders. And so I've done a fair amount of work handling, trying to address malicious and selfish users. In this talk, I'm going to focus on providing incentives to these selfish users, and then encourages new tools of the trade. So first, some new assumptions. Rather than assume altruism, we're not going to assume altruism. We're going to assume that participants want to gain the most from the system and will lie, cheat, and steal to get it. So they're rational. They will perform in a way that will get them the most from the system, and they want to get at the potential expense of others. That could be because they just have complete disregard for other people's performance, or it might be the case that they just don't know what the impact is on those other participants. And so this also motivates some new mechanisms, and that's really what I'm going to be talking about today, is the application of some economic mechanisms, in particular auction theory, to real practical systems. We want to build these systems with this nice theoretical foundation of auctions. And there's two things that this is going to give us. It's going to allow us to fairly allocate some scarce resources, bandwidth, links. We're going to get into both of these types of things. But that's not all. So not only do we want to fairly allocate them and be resilient to selfishness, when I try to apply incentives, I also do it in such a way that I try to improve the performance of the system, predominantly by encouraging others to contribute more to the system. And as I mentioned before, the system is of the users, for the users, and by the users. The more they give to the system, the better the system's going to be. And one of the key insights that I'm going to show here, some of the main technical challenges that arise along the way, is this problem of, as we take this discipline of economics and this discipline of systems, to get the best of both worlds, systems we can really build while being able to prove things about the economic side, we have to align the assumptions of the two. And so these are going to be some of the common themes and things that come up throughout the talk. So I'm going to talk about two pieces of work here. First, I'm going to talk about BitTorrent, and I'm going to show that it is an auction. And the point of this work is to show that auctions are a very natural mechanism, a natural way to think about these systems, and they sort of occur naturally even when they're not explicitly designed into the system. Second, I'm going to talk about a new system that we developed from the ground up that explicitly incorporates auctions into the very fabric of the protocol. And it's more of the technical considerations that come into play when putting these auctions into practice. So first, BitTorrent. BitTorrent addresses the following problem of what's called bulk transfer. The problem of bulk transfer is to distribute a large file to a large set of users. Now, the traditional approach would have a centralized server where all the users perhaps try to download from that. But the problem is that the more requests there are, the less bandwidth each one of these users can get from the centralized server. So as a result, we have slow performance for each of these users because the server is overloaded. BitTorrent is an example of a file swarming system, which is the following thing. Instead of each user downloading the whole file from the server, some of them download pieces of the file and then trade with one another. And so this is much faster because we put the users to work. On the left side here, we had a lot of unused resources. The users had these uplinks that they just weren't using. BitTorrent puts it to work. As the users demand, they also give back to the system.
Do you really think it's faster or it's just cheaper?
It is faster. Absolutely. From just compared to just everybody downloading from a centralized server. Of course, you could attempt to provision the server much more to get comparable downloads. But at the same time, no matter how much you provision that server, I think that if the users contributed as well, you're going to get performance improvements. So that's been shown.
Why don't we see big companies working this way, right? Most of the uses of BitTorrent is to steal things. But if you look at, say, pick something that gets lots of traffic, like the Windows Update site, it doesn't work that way, right?
Increasingly, they are turning to this kind of...
Yes, but they don't do peer-to-peer.
Increasingly, they are turning to this. So, for example, I think one of the biggest examples is World of Warcraft uses this kind of approach to distribute their updates. Yes. So that's exactly right. So because you're putting the users to work, that's less work that some centralized service would have to do. So you're right that it absolutely is cheaper to get comparable levels of performance. But additionally, by putting the users to work, you also get improved performance. So
that's debatable.
Yeah. Okay.
So just to push back on the faster, I also don't buy into this faster thing. I don't know if you saw the New York Times or whatever yesterday, where it said the national broadband plan is 100 megabits to 100 million homes, right, for the next 10 years. And with the substrate getting so fast, I don't know how it would be faster. In what way would it be faster?
I'd be happy to discuss this a bit more, but I would argue that as many of the experiments have shown, and as we'll see, that by manipulating this protocol and by manipulating how these users do share with one another, we can see improvements in terms of in the performance.
Who are your stakeholders?
Who are the stakeholders here?
Yeah.
So within the context of this first piece of work, I think of the stakeholders as being the users themselves. And so one of the actually sort of surprising things here is that you would think that they don't have competing interests. They're all in this together for good reasons of getting updates of Warcraft or other reasons, as some may point out. you'd think that they're aligned, that their goals here are aligned, but in fact, because they want to download as quickly as possible, there's going to be some competition there. There are as well, perhaps depending on the content, for example. But I'm mainly focusing in this talk on the exchange, so the competing interests between the users. So what users make up a BitTorrent system? So there's three different kinds of peers in the system. First are the seeders, who have the file and who upload to others. Second are the leechers, who have some pieces of the file and are actively downloading it. And last are the trackers, who introduce new leechers to one another. So for example, a leecher joins, contacts the tracker, gets put in touch with some other leechers. So this talk I'm going to focus on the leechers, those who are actively attempting to download the file. And I'm going to assume two things about them. First, that they're selfish, that they want to download as quickly as possible. And second, that they're rational, that if we have a better strategy, that they will employ it. And I'm going to actually show some results that demonstrate that they have incentive to deploy some of these better results. And their goal is to download as quickly as possible. So let's look at, yes?
Do you have any evidence that the peers in BitTorrent are rational?
That the peers are rational. So a couple things about that. One, I think that the system designers who create the clients wish to develop rational clients. And secondly, it provides this foundation, this theoretical foundation, by assuming selfish and rational, that's going to allow us to evaluate what kinds of approaches they would take. So I would say that in any, say, given instance, there might be things that happen that would be, say, bugs or poor design decisions. But they're rational in the sense that I think that given the better alternative, they would certainly seek that better alternative. And so by thinking about it in that way, it's going to allow us to see, given a strategy, what are some of the ways that we could manipulate it, and over time that we would expect to see that manipulation.
The system designers would want the clients to be altruistic, and it's people who do funny clients who would be rational, right? Because the system designers of BitTorrent are trying to optimize overall throughput rather than individuals. So it's people who are making cheating clients that would be rational. Is that what you meant by system designer? Or?
So two things in response to that. I think that assuming that they are altruistic is perhaps not necessarily the case. I think that as people make different clients,
designers would want to make,
or that they would want them to be altruistic. I think that one way the way I sort of think about it is that everybody sort of wants to create the fastest client. And so if it can benefit the user, potentially not at the expense of the rest of the system, then they would prefer that. And I think that we've seen over time that certain people set, say, like how long they're going to seed once they lift the file to certain levels. That I would rather, returning to my view, rather than enforce altruism or design a client that enforces it, I would rather design a system that provides the incentives to give. Right? Absolutely.
Maybe I'll ask the question differently.
Sure.
So have you, are BitTorrent clients, client software being manufactured by, being written by different authors? And do you observe some to be more selfish than the others? Or?
So there's actually a recent recent news article with uTorrent, a very popular client, that some in the BitTorrent community have deemed that its new trading strategies are unfair. And so you actually see some trackers blocking the uTorrent client. So I think that there absolutely is this notion that their kind of unfairness, just to mention it briefly, is that it would appear that they're treating their own peers, they're favoring their own peers over others. So returning to this notion of a leecher, the peer in the system who's downloading the file, there's three basic steps in the life cycle of a leecher. So if we think of time going down into the percent into the download, the leecher starts off without any blocks. So they have to get some blocks for free from some other peers or from some other leechers or seeders. But then they enter, once they have a few blocks, they enter what's called steady state. And that constitutes the vast majority of the download. And that's where they're trading pieces of the file with others. Finally, in the last few pieces of the file, they enter what's typically called endgame, where all bets are off. I'll lie, cheat, steal, because as soon as I get those final pieces of the file, I don't care what you think about me. You can find out that I'm a cheater because I'm out. I'm done. So we're going to focus on is the steady state, what constitutes the vast majority of the download. And there's a few different policies that a leecher could make in regards to how they approach steady state. The first is what do I download? So I have multiple neighbors who have various pieces. Which pieces should I request from them? So the standard approach is to estimate how rare these pieces or blocks of the file are, and to request the rarest ones first. So to prioritize the rare blocks so that we don't end up in a case where all of a particular piece of the file has gone away from the network and we all have to start hitting the server, or at least some of us have to hit the server to get that piece. The next question is, to whom do I upload? And this is determined by what's called an unchoking algorithm. So this is going to say how much bandwidth do I allocate to each of my various peers, each of my various neighbors. Last question, and this isn't a question that's typically asked when considering incentives in BitTorrent, is, well, what do I upload? And the reason this isn't asked is because the standard practice is to state everything you have. And this would seem very intuitive. If I tell everybody what I have, then maybe they'll be interested in me and they'll actually want to trade with me. But I'm going to show that there's actually a way we can manipulate that. And so this is determined by what's called a block revelation strategy. And I'm going to talk about how we can manipulate that. So the two things I'm going to talk about in this talk are analyzing the unchoking algorithm, the decision on to whom do I upload, and how much do I upload, and also this notion of what do I upload with the block revelation strategy. So first, let's talk about BitTorrent's unchoker. BitTorrent's unchoker is a round-based algorithm in which in each round, a peer can receive blocks from other peers and also gives blocks to others. So consider this case where this is a peer who received various amounts in round T. What BitTorrent's unchoker does is it sorts them, and in the following round, returns back to the top 4 uploaders from that previous round. And it returns equal amounts of good to each of them. Now, this has traditionally been described as being tit-for-tat. And tit-for-tat is a little bit of a conflated term. And so let me explain why that sort of raised a little bit of question. So tit-for-tat on the one hand could just mean, hey, you give to me, I give to you, and that's that. But there's also a rigorous game theoretic term, tit-for-tat, which defines a strategy in which, in a round-based game, if I play tit-for-tat, that means in the current round, I do precisely what you did to me in the previous round. And so it's well known that that game theoretic construct of tit-for-tat is, you can't game it. It's a very, very good strategy for a large class of games. And so it's broadly considered, hey, if BitTorrent is tit-for-tat, then it must also be resilient. But if we look at this, we see that's not exactly what that is. There are many peers who gave to me, and I didn't give anything back. And what's more, there's peers who gave more to me than I gave back to them. I gave equal amounts of good to them, despite the fact that they gave different things to me. So what is this? If it's not, it doesn't seem like it's tit-for-tat, how can we best describe it? Very sorry, so this quick run through tit-for-tat. How can we best describe it? And that's that it's an auction. So what is an auction? An auction consists of 3 basic things. First are bids. And the bids here are the uploads from the prior round. The second thing is goods. What can we potentially win from that? Those are the next round's uploads. And the third component of an auction is the clearing mechanism, how we map bids to goods. And in the case of BitTorrent's unchoker, the auction clearing mechanism is top 4. Now, this isn't exactly an auction that I think that you're going to find in the auction literature, because it turns out it's not how you would run an auction. By thinking about it this way, you see that the issues that some in the related literature have pointed out is really because of this auction clearing mechanism. So let's look at a couple ways in which we could game it. So suppose that I'm the red peer, D for Dave, and I'm bidding in this auction. So what are some things I could do? Well, suppose I was willing to actually give more. I want more from this peer. I'm willing to increase how much I'm uploading this person, even if there's just some marginal benefit to that. And yet there's no impact on what I receive. Okay, so there's no point in giving any more. How about giving a little bit less? Well, of course, there's this threshold that as soon as I drop out of 4th place, I lose, but if I can just give just enough to stay in 4th place, then I'm going to hold on to the amount I win. So there's no point. As soon as I'm in the top 4, I have no incentive to give any more beyond that. So there's this incentive to cheat, which is to come in last place. And that's precisely the insight behind the BitTorrent client. And I think that when viewing it as an auction, it just becomes very clear why that strategy works. Yes?
What are you doing? But typically you don't, if I'm D, I don't know how much A, B, and C are going to send.
That's right.
I don't know what.
So fortunately, this is a round-based protocol. And so for instance, what BitTorrent does is it adjusts how much I bid to try to see where I could come in last place. This has a couple assumptions, like, for instance, that the amount of contributions others are giving are roughly stable, and that if they are roughly stable, then by feeling it out, by adjusting it over rounds, then I could attempt to come in that last place.
And these are practical assumptions, like do they hold often in practice, or these are?
It would appear to, given BitTorrent's performance, given the fact that it does perform well, I would think that those would be reasonable.
There's other things also going on, right? It's not just this.
That's true. One of the other factors that some other researchers have pointed out that greatly assists is the fact that it opens more connections than 4. But at this point, I don't know the extent to which of those two factors ends up providing the most benefit.
Does that also rely on the density of BitTorrent being low? That is, it's not competing against itself very much.
Oh, actually, so it would actually improve if there were more BitTorrent peers, because they treat one another differently, actually somewhat similar to this. That's right. They assume there's some means of communicating their identity, their peer identity. So another way that you could potentially game the BitTorrent protocol, or the unchoking algorithm, is as follows. So suppose that I was willing to give much more to try to get something back, and so I could launch a Sybil attack, courtesy of JD, of course. And the way in which I could do this would be to contribute just enough to come not only in 4th place, but also 3rd and 4th place, in which case both of my Sybils get within the top 4, and now I end up getting twice as much contribution. But this seems kind of weird. There was a way for me to get more from this peer, and yet I had to go about this method of submitting separate bids, creating these Sybils, and contributing much more. So this just doesn't seem like a very natural thing. It would be much nicer if there was a way to get some back without having to manipulate these strategies.
In that case, it costs you more than twice as much to get twice as much return, so it's sublinear also.
Yeah, and what's more is there's also various additional control messages and so on. So how might we go about designing a better auction? So the first thing that we'd like to have, the property we'd like to have from such an auction is that it provides incentive to give back to the system. So early on, I worked on a system called Fox, where what we tried to get was perfect fairness. For every bit that you gave, you got a bit back from the system. The issue there is that it's kind of a fragile system, and also if there are peers who are willing to give more, if there's exact bit-for-bit fairness, then they can't necessarily get anything back if there's not enough capacity in the system to give back to them. So we go for a somewhat looser notion of fairness, which is going to get us actually much stronger properties, and that's that the more you give, the more you get. Now, if we have this kind of property, now all of a sudden we do have incentive to get more or to give more to the system, because as a result, we'll download faster. And what it's going to allow us to do is it's going to allow us, our first sort of insight into the practical application of auction theory. And there are a few concerns in doing that. As I mentioned earlier in the talk, we need to align these assumptions. So there are a few assumptions that are somewhat common in some auction theory that we're not going to be able to make here. The first is that we're not going to have perfect information. We're not going to know exactly what the contributions of others are. There's not going to be one central clearing house. And also, we kind of introduce this other notion that we want to not modify the BitTorrent protocol. How far can we get by just modifying the local policy? The auction mechanisms are already there. How can we just change the policies to improve it? And there are a few questions that are going to come up. Yeah.
With the more you give, the more you get strategy, where if you give twice as much, you'll get more, but not necessarily twice as much. Doesn't that encourage Sybils then? Because you could just create 2 Sybils and you would actually get twice as much.
It's going to depend on what that return is. So I'll address the Sybil attack in just a few slides. So by applying auction theory, there's going to be a few questions to keep in mind. First is, how do I bid in others' auctions? What auctions should I run? And last, how do I advertise my auction? I want people bidding in my auctions. How do I get the word out that I have a good auction to run? So the auction that we use is the well-known proportional share auction. Here's how proportional share works. It's also a round-based protocol, so we're going to fit right into the mechanisms. And the amount that I give to one of my peers in round T, in the current round, depends on the proportion of contribution that he gave to me in the previous round. So the amount that he gave to me divided by the total amount that I got. So for example, suppose I'm the blue peer. I've received 150 contributions, say pieces, in the previous round from everyone else. And this red peer gave me 50. not of that, so 50 more in addition to that. So that means that this peer gave me 25% of my total contribution that I received, and in response, I will give 25% of my bandwidth that I can give to him. Now, what this means is that it does seem as though they're kind of giving equal amounts, but I'm giving 25% of my bandwidth, which might not be at all comparable to what he may have given to me. It might be more, it might be less, but proportionally, it ends up being the same. So let's take a look at what happens here. Well, now let's say I manipulate my bid again, I increase it. Well, as a result, I will get more as a result because my proportion goes up. And if I decrease that bid, my proportion that I contributed goes down, and so I get less, everyone else gets more. So we have this nice property here that the more you give, the more you get. The greater you give, the greater the proportion, greater the return is. Now, returning to Jay's question, what about Sybil attacks? So I'm going to show that actually it's resilient, it's Sybil proof. So suppose that this group of peers have contributed a total of 30, and that I wish to submit a bid of 50, but I decide to split it up into multiple Sybils. Well, let's see what happens. I send 10 through each of my Sybils. As a result, this peer received 80, and so each of my Sybils got, whatever they contributed divided by 80, and of course, add that together, and that's precisely the 50 over 80 that I would have contributed in the first place. So by constructing precisely what that response is, that's how we're going to be resilient to the Sybil attack. And so in this case, you have no, as we mentioned earlier, because there's additional control messages, there's no incentive to launch a Sybil attack. So next question is, how do I bid in a prop share market? Imagine we're in a world where everyone else is running prop share, and I want to decide how to bid. If I had perfect knowledge, I would see this curve here. Okay, so this is a bid being run by a yellow guy. The amount I give results in the amount that I would get back, defined by a curve like this, asymptote at the bandwidth and diminishing returns throughout. So there are actually multiple auctions going on here throughout the system. The question is, well, how should I bid in them? Let's assume that I knew these curves. Well, the question is, or the goal here is to maximize how much I get by using a fixed budget, which is what my upload bandwidth is. And the solution here would be, if I knew these curves, would be to find the point on each of these curves such that the slope is the same and that I've used all of my budget. Very simple to do, great, but the problem is we don't have these curves. All we have is local information. So what's the best thing to do? Well, one of the interesting observations here is note that the more I contribute, so the longer these bars are, I gave the most to blue, the least to purple, also corresponds to how much, in terms of rank, they gave to me. So it seems to exhibit a very similar prop share kind of approach. And so I evaluated this and compared best response, assuming that you knew the curves, versus just straight up prop share without knowing the curves. And it turns out that although the allocations can be quite different between those two strategies, responding with prop share, responding with this best response, the end result, the amount of utility you get, ends up being almost identical. And the reason is because that the differences end up being sort of in this space of marginal utility. So it turns out that the best response to a world of prop share is to play prop share as well, assuming that you don't have local information. Helen, you had a question?
The question is that if I'm a bidder, and I know this guy does not have a lot of bandwidth, so I may choose not to bid for those clients who have a very low amount of resources. So would you create segmentation of your network? So the resource-rich peers, they will bid with one another, and the resource-poor clients, they almost form separate networks.
That's a fantastic question. Thank you for asking that. So that's some ongoing research right now that we're looking at in terms of how do these peers end up clustering, and are there certain incentives we could provide that may result in better clustering. So you could imagine, for example, maybe we do want the high-capacity peers trading with the low-capacity peers. At this point, it's an open question to me what the ideal clustering would be and what happens by default. But that's some questions we're looking into now. Yes.
I guess maybe this right. How does this perform under churn? If I have a high-capacity peer coming and going in my bidding, then that high-capacity peer will be a lot of my prop share. And then I'll start starving the other peers, which will self-starve me. And if the high-capacity peer goes away, then we could end up in a situation where we're starving each other because of previous rounds.
That is a concern. I haven't looked explicitly at churn, so the types of experiments which I'm going to show in just a little bit assume that the peers join at roughly the same time, and then as soon as they're done, they leave. But in terms of these kinds of dynamics, I haven't looked exactly at that. You could imagine certain scenarios where there's this huge capacity peer that would cause these kinds of issues. But in practice, it seems as though there are some high capacity peers, but then some of the load ends up being sort of distributed. So I haven't seen these kinds of churn effects, but I also can't say that I've delved into really putting that under the microscope to see if that happens.
There's a little bit I'm missing here in a sense. It seems you're projecting like responding to bidding as independent decisions being made. But it seems like my bidding is actually in part response to the bidding that happened in the previous round or in my auctions. So where does that coupling show up? Like, the amount I send in this round is like not independent entirely. It's not,
Sure.
So where does that coupling show up in the decision making here?
Right, so that was a concern. Before I knew this result, that the best response to prop share was prop share, I was concerned because if it turns out that the best response is vastly different, then what's going to happen to the market? Why would anybody be running prop share if everybody has this incentive to unilaterally defect from what everyone else is doing? But because the best response in practice ends up being the same auction that we wanted to run in the first place, that's where it ends up coupling. Why does that happen? Does that happen with other kinds of auctions? These are also open questions that I'm quite interested in looking into and would be happy to discuss some more.
Practical effect here that I haven't seen in the model, which is that you're not really bidding money, you're sending bandwidth over a network link.
Sure.
And so if you've got somebody who's got a high upload bandwidth, then this algorithm is going to cause lots of people to want to send data to them. And congestion control is going to back off, and you're not actually going to be able to meet your intended bid. You just won't be able to send the packets because link will saturate.
That's an interesting observation. I haven't observed that. I think that what would happen would be that it would adjust, but I don't want to speculate as to what might happen in the case of severe congestion.
In the real world of peer-to-peer things, link bandwidths are asymmetric. So you've got a lot more download bandwidth than you do upload. And over a set of peers, the bandwidth of the system is going to be the minimum of the sum of the two, right? Because the data is all going to come somewhere and go somewhere.
Sure.
But in a system like this, if you've got a little more upload bandwidth, it seems like people are going to prefer to send to you because you can give more back. And there might be an instability in the system there, where if you have a little more upload bandwidth, everybody's going to want to send you because you've got more to give back.
Well, so also keep in mind that as soon as many people start coming to me, then their overall proportions are going to start decreasing. So I think you would see this balancing effect.
But it's going to push that asset up, right? The asset is essentially the upload bandwidth of
that's right.
That's right. Not the bidder, but the other side of the auction, right? The seller.
Auctioneer. Or the seller.
It's the seller.
Sure.
And
so in general, do you see any oscillation? I mean, a lot of the questions seem to be like, do you see any instability or anything like that? Have you seen any of that empirically? And why do you think that is?
A little bit from round to round, just because of the natural dynamics of prop share. So I give to you one round, and if it's always based on the previous round, then you gave to me, then the next round I give to you, and so on and so forth. And so to overcome that, we just take a weighted average over a couple rounds, and that ends up adjusting that. But otherwise, I haven't seen this kind of instability.
Did you model asymmetric bandwidths?
We
limitations based on these network bandwidth.
We deployed this on Planet Lab and also on Live Swarm. So yeah. Did it for real. Does it work for real? Yes.
So in response to Helen's question about shouldn't everybody prefer to send to the high bandwidth guys, you said that it would you implied that it would wind up clustering low trade with low and high trade with high, but it seems to me like it would wind up lows don't trade with each other, lows trade with highs, and highs trade with highs.
Perhaps. I'm not sure what that clustering would be at this point.
That's what happens. And that's what everybody reports. It's peer-to-peer really is stuff, but lows trade with highs.
Lows trade with highs, and highs just kind of trade with everyone, I guess.
They're like super peers.
I see.
Yeah.
Hey, isn't Untitled Lab not actually has this problem that it doesn't have asymmetric bandwidth as much?
So we could cap the uplink bandwidth on these, and so we cap the uplink bandwidth according to the distribution that was measured by some of the BitTorrent authors. So we implemented this our prop share client within the Azurius BitTorrent client with a few questions in mind. The first was, how does it play with BitTorrent? So for that, we ran some experiments on live downloads, downloading on live swarms. And also, we wanted to look at some controlled populations so we could see what would happen as the dynamics, as more and more users, say, started using prop share, and also how does prop share react to other kinds of strategic clients. So how does it fare in live swarms, consisting of presumably all BitTorrent clients? So there could have been, say, some BitTyrant, some other kinds of clients, some other various manipulations, but just in general from the BitTorrent community. And so to run this experiment, we ran 3 clients simultaneously from within our network at University of Maryland. First, as a baseline, was BitTorrent. We also ran the BitTyrant client, which is, recall that explicitly games the BitTorrent protocol. And last was our own client, so our prop share client, which is oblivious to the BitTorrent protocol. It just runs straight up prop share against whatever strategies other peers might be running. So this is, I'm going to show some results which are across a little over 20 different downloads. And what the y-axis here is the fraction of this client's via BitTyrant or prop shares download as a fraction of the BitTorrent client's download. So a value of 1 would mean it performs precisely the same as BitTorrent. Above 1 is worse. Below 1 is better. And what we see is that prop share ends up performing very comparably to BitTyrant. So even though it is oblivious to the BitTorrent protocol, it ends up performing very similarly. And so this is great news. This means that today users would benefit from using the prop share client. So I just want to give a brief overview. Yes?
Were you downloading from the same clients or not?
I'm sorry?
When the BitTyrant client and the prop share client, did they download the file from the same other peers or no? I'm just wondering whether the changing network conditions would play any role in this.
Sure. So to mitigate that, so rather than try to, say, enforce who they might be trading with, we just ran it on multiple swarms. And so this was something that we see across these different swarms. What's more is we also just changed which computers were running which one, but they were all from the same University of Maryland network, so it should have been from the same distribution. So just to give a quick overview of some of the other results from these experiments. So I showed that single client prop share performs very similar to BitTyrant. In our controlled experiments, we showed that prop share is resistant to various forms of manipulation, and that as more and more clients, more and more peers start deploying prop share, the overall performance of the system increases. I wanted to talk about one other component of this work in
What metric do you mean the overall performance of the system increases?
the overall download time across the system.
The total bandwidth expressed in the system increases. It's not a measure of fairness. It's just a measure of utility.
That is not a measure of fairness. I think perhaps you could try to extract some notions of fairness from that, but
all right.
So I mentioned this other sort of vein in this work of BitTorrent, which is advertising an auction. The thing to note is that peers only bid in the auctions that they're interested in. So imagine this is a red peer, and this is to keep track of who they might be interested in. They keep track of what's called a bit field. And so this bit field contains information as to what pieces of the file this peer has. This peer has blocks 0 and 1, but does not have block 2. And so periodically, peers exchange this information with one another so they can determine whether or not they're interested. So in this case, the red peer sees that the green guy has a piece of the file that he does not, so he's interested. Likewise for the green guy, and so they open up this opportunity to trade with one another. Now, if we think of this notion of who's interested in whom, you can imagine various kinds of interest configurations that would be more or less preferable to a peer. So imagine I'm the red peer. The least preferable thing to me is when nobody's interested in me and everybody's interested in everyone else. Everyone is making progress through the protocol, and I'm not seeing any of it. The most preferable thing would be that for anybody to make progress through the protocol, they have to come through me. So all bandwidth contributions could potentially come through me. So the first goal in advertising our auctions in terms of gaining this interest is to be interesting. So let's take a look at what happens. So recall from earlier in the talk that I mentioned that the standard practice is to state everything that you have. So again, I'm this red peer. I have the yellow and purple blocks, and I have these two peers who are interested in me because they don't have these blocks. Standard practice is I say, hey, I have yellow and I have purple, in which case they could each request different blocks from me. In so doing, now they've essentially decoupled from me. They don't need me anymore because they're interested in one another, and they could exchange with one another. So what happened here is that I actually moved into a new interest configuration that's somewhere between the two. They could be trading with me, but in this case they're not because they traded with one another. So there's this new interest configuration somewhere in between in that people can make progress through the protocol without me. So it introduces this other goal that would get us into the better configuration, which is not only to be interesting, but to somehow keep others from being interested in one another. I want to be the coolest guy on the scene that everybody wants to come to for anything to get ahead in life. So how might we go about doing that? Well, let's throw away the standard practice. Instead of stating everything we have, let's just state we have one of these pieces. In which case now they both have to request the same thing, at which time I can say, oh yeah, by the way, I forgot to mention, I also have the purple block. And now I've maintained this coupling to me. They didn't gain interest in one another, they have to download from me. So as a result, on the right side here, we maintained our ideal interest configuration had we do that by strategically under-reporting the pieces that we have. So not only are we not going to state everything we have, we're also not going to lie and state we have things that we don't have. We're going to be better off by under-reporting the things that we actually have. So this gives rise to a very natural strategy, which is when one of my neighbors loses interest, that's the point when I'm going to reveal something to him. What should I reveal? Well, I want it to be actually the most common piece that I have that he doesn't have, so that when he does get that piece, he doesn't gain interest. He doesn't gain others' interests. So he implemented this strategy as well. Here's an example with one strategic revealer. So the x-axis is time into the download. The y-axis is the fraction of peers with mutual interest. So what fraction of my neighbors who I have interest in are also interested in me? So the ideal would be 100%. And we see here is that this strategic under-revealer reaches this peak very quickly. He gains interest, he holds on to that interest, and also ends up downloading the file much more quickly. So it drops off where the file has finished downloading. Unfortunately, as more and more users start to employ this strategy, it's better for one guy, but ends up leading to a tragedy of the commons. So what we see is that peers waste all this time saying, hey, I have piece 5. Hey, I also have piece 5. Okay, 6. I do. 7. They keep going on until eventually they finally reach this point where they can see this negotiation. And we see an overall increase in the download times. So what's interesting here is, we approached this problem and tried to solve it with incentives, and it seemed like we just couldn't figure out how to solve it with incentives. And so for a while, until I started my internship here, this was an open problem to us. And once we started here, we worked on this other piece of work. So I don't want you to be too worried about how to solve this problem. So I'm going to just mention very briefly how we went about it. And the thing to note was that it was a security problem disguising itself as an incentives problem. And that security problem was what's called equivocation. So in a large distributed system, even a small distributed system, a selfish or malicious user could equivocate by sending conflicting messages to others. So for instance, I have received your vote, or I haven't received your vote, or report a tally without that vote. And then the case of BitTorrent, what this results in is to one peer I say, all right, I've received that piece, that purple piece, when I acknowledge having received it, but then later on I underreport it and don't state it. And so to address this much broader problem of equivocation, we designed what's called Trink, which is a small piece of trusted hardware that ends up demonstrating that a small trusted counter is enough to solve this problem of equivocation. And the nice thing here is that it achieves, because it's so small, because it's minimal, and that's what ends up making it much more practical. Question, just a sec. Just want to bring up this last thing, which is that equivocation is a much broader problem, and these are just some of the other applications that we applied this to.
So your example before, the guy didn't equivocate. He sent the same message, I have purple.
He did. So the thing to keep in mind is to take a step back in time and say that when he got that purple piece, he acknowledged having received that to the purple peer, whoever gave him that purple piece. So he told one person, I have received it, and then told these other two, I've never received the purple piece. Okay? Yeah.
Why don't you use Trink for everything? Why use prop share just in the first part of the protocol where you are trading blocks? Why is Trink not useful there as well?
I'm failing to see where that ends up being a problem of equivocation, but I'd be happy to talk about that a little bit more with you offline. In a broader sort of philosophical sense, in terms of why not, perhaps one of the things that you're getting at is why not put a small piece of trusted code to enforce what peers do. which is maybe one of the things that you're getting at there. And again, I would return to this notion of, it's a network of the people, for the people, by the people. And so rather than enforce it, I would like to open up the ability for them to express their own local policies in a way that may benefit them and ideally would allow us to progressively deploy better and better protocols.
So that's what I'm trying to struggling. What's the difference between enforcing behavior in this context and not enforcing behavior in that context?
Right. So
you either philosophically, you either go incentives or go enforcement and pick one.
Sure. So I think that to summarize, it's that incentives do give us a lot. They give us this ability to understand the protocols that we're running and that we're designing, and they can get us these strong properties like fairness and resilience to the Sybil attack, but they don't necessarily seem to get us everything. And so there's other techniques that we seem to need in order to solve a broad class of attacks. And so I think there are some things that we can encourage that users or peers do, and there are others that it would seem that no amount of encouragement would solve it, and that we actually do want to stop certain things. And so my general approach is, eliminate the possibility for a small class of things and try to provide incentives for another broad class. Yes?
Have both incentives and enforcement in real life, and one without the other is not sufficient?
If I can interject here, we're kind of running a little late. I know Dave's got a lot more stuff to talk about, so particularly those of you who are going to interview him, if you could hold your questions for the interviews. Thank you.
Can I just get a time check? Is it?
Keep going.
Okay. All right. So we move on to the second half of the talk, which I'm going to try to move through rather quickly here. And so,
if you could get through this in 20 minutes, that'd be wonderful.
Okay, great. And so it's this notion of what a system that we call Hoodnets. So I just talked about BitTorrent and how providing incentives at this application level, this peer selection level, could end up getting us nicer fairness properties and better performance overall for the system. So I've been largely interested in, well, could we take some of these things that we've learned and push them down a level? Could we see what happens at the level of forwarding in the internet? Can we get incentive-compatible forwarding? So the thing to note here is that in the internet, links are a scarce resource. Actually, in the history of the internet, it used to be the case that links were the cheap part, and that the switching technology was actually much more difficult, which is why now which is why we used to have circuit switch networking, and now as we move to the switching technology being much easier, we've moved, of course, to packet switching. So links now are the scarce resource. And so here's an example of an overloaded link here. And what we would like is, if we aren't able to service all of the demands, we'd like some way in which users or end hosts could somehow express the value of their packets or the priority of their packets. So for example, suppose the green packets here are of high priority or of high valuation, the blue are lower. What we'd like to be able to do to get the most social good social welfare out of the system would be to prioritize the high value or high priority packets and send those along instead. So this is a notion that has received some attention over the years in terms of how to maybe apply auctions here. And so what the nice things that auctions give us is they would elicit truthful valuations, how end hosts value their packets, what the priority is, because otherwise everybody's just going to say they value it 100,000% all the way. So there's been a fair amount of work. So this is just some of the pieces of work over the years, over the past 17 years. But that has largely applied to the wide area internet. And so one of the things that's, that I approach a problem like this and I say, I could approach it from the wide area internet, but what I really want is a playground in which we can put these ideas and these mechanisms to work. I want to build these things, evaluate them, and ideally, in a way, in an environment in which we can get a tangible performance improvement. And so rather than focus on the wide area internet, I'm going to look at a lot of these same problems on sort of the last hop here. And that's in terms of how to get better use out of cellular data networks. So increasingly, we see these mobile devices that have dual interfaces. They have a cellular interface, which has the great benefit of broad coverage, but typically has low bandwidth. And on the other side, we have these Wi-Fi links, which have very little coverage, but extremely high bandwidth. So the main mechanism that we're going to use to get better use out of these cellular networks is a technique called channel bonding. Channel bonding has been around for as long as there's been slow links with a high-speed backplane. And in this case, this is exactly what we have here. We have these slow cellular links, and we have the high bandwidth backplane of these Wi-Fi connections. So imagine as a sample scenario, you're on, say, one of the buses out here, and you're sitting there, you have your iPhone or maybe an eVideo card in your laptop, and you wish to get better bandwidth. And so you form an ad hoc wireless network, which is your high bandwidth backplane, and then you start channel bonding. What does it mean to channel bond over these links? It means to send my packets not only over my own link, but also along other people's links, these neighbors' links as well. Now, achieving channel bonding in the cellular network is technically very challenging. And so this is one of the main sort of big moving pieces in the system I'm going to present called Hoodnets, is how do we get this? How do we get performance despite the variability of these links? So they have high, often variable latency. Coverage can be very spotty. So just to kind of show, that nice picture that we had before of these packets arriving in order going along these links might be very different. The latencies could be different, and also links can go away, in which case some of my packets may be dropped. As if that wasn't hard enough, of course, we're looking at this selfish environment. I'm sitting on the bus, I have my cell phone. Why do I want to let you have access to my link? It's going to drain my battery, it may cost me money. How do I address these users' concerns? Why do I want to forward for you because of these concerns? And also, why do I want to forward through you? Because there might be security concerns. If somebody forwards through me, they may try to launch an attack, making me look like the source. And so one of the key insights here, one of the things I'm going to argue, is that to achieve both of these things, to achieve high performance and to achieve incentives, that we have to design both together. I'm going to show that here by demonstrating the philosophy. Oh, goodness, I'm very sorry. Of this. Sorry, let me. There we go. Very sorry. Okay, so taking a closer inspection into one of these cellular devices. Yeah.
So the motivation here is to increase the bandwidth of other network or to increase the bandwidth of my cellular connection by using your cellular connection?
That's exactly right. So for both of us to be able to share our cellular links. So taking a closer look into one of these devices, we're going to see that there's some application, a queue for my packets, a queue potentially for other people's packets in our two interfaces. And suppose we're in this case with this network, this sort of deployment scenario where I have some packets here, two peers on the left who have packets they wish to send, and one peer on the right who doesn't have anything to send. And so this is where we're going to get this space to play in, where I'm going to be able to purchase some access to somebody else's link because they're not actively using their device at the time. So a few goals here. So sort of the philosophy on what we should be able to get in terms of incentives. The first is that end hosts should be able to express their valuation, both in terms of their packets, how much they're willing to spend to have their traffic forwarded, and also in terms of how much they want to charge for allowing access to their link. So this is going to be a packet valuation, then this little stop sign here is going to be a reserve price. So I'm going to stop all traffic coming through that doesn't meet at least this price. The other thing is that relays should be allowed to forward profitably. They shouldn't have to do work for others if they don't feel like they're getting compensated enough. So here's a quick example. Suppose that this peer submits a packet. He should be able to reject a packet if it doesn't meet his reserve price. What's more, if he has multiple packets in queued, he should be able to give preference to the higher valued packet. Now, these two perfectly reasonable incentive goals give rise to a very real technical challenge, which is that we're not going to be able to do connection pinning. So there's been some prior work which has looked at channel bonding these types of links, and a very common approach is to, when given a TCP connection, to pin it to one of the neighbors and to send all packets corresponding to that TCP connection through that neighbor. Well, why is that? Why could that be a bad thing? Suppose that the blue guy had pinned his connection to this guy on the right. Well, now because everybody should be able to express their valuations and be able to update how they value and their own resources, that peer could update his reserve price to $4, in which case now he's not willing to submit this packet anymore, to transmit this packet, and could drop that packet. So we need to be resilient to these kinds of changes in valuation. And these are the broad goals and properties of Hoodnets. So end hosts can express valuation. No participant has to do more work or pay more than they're willing. Hosts run profit maximizing auctions, and also rather than pin a connection, we restripe TCP connections across multiple links and make forwarding decisions on a packet-by-packet basis. I'm sorry?
Two ends. You control the receive side and the send side.
Oh, so that's exactly what I'm going to get to in just a sec. Yes?
Yes. So it seems to me that the hardest problem here is the first one. Okay, how is a nethost able to express? How is the nethost ever going to evaluate access? Put values on its packets or its forwarding capacity? And it seems to me that your talk is going in the direction where you're going to focus on the last bullet or probably the last two bullets.
The middle bullet is what I'm mainly going to focus on the auction.
It seems to me that you're sort of sidestepping the most difficult part about how you assign a value to a packet or how do you judge the cost of forwarding it. That's where all the cost systems go to die, right? That's the rock on which they go to die.
So there are a few reasonable valuation policies that we have come up with. In a sense, I didn't want to tie the system to a particular policy. But I'm going to talk about a few different things that these mechanisms get us. They're going to open up the space for these kinds of policies. What should the exact value be? Should it be, I'm going to speak in terms of dollars. Should it be dollars on a packet-by-packet basis? Certainly not. But the precise valuation and a really good, clean way for users to be able to express it without having to, on a packet-by-packet basis, say how much they're willing to bid, are absolutely open problems. And I'd like to discuss that a little bit more. But you are right in that we are going to be assuming for the remainder of this talk that they have some sense, that the end host is able to attribute some valuation to the resources. And I'd be happy to discuss it more offline, but I'm not going to be addressing it just within the talk, though. Yeah, sure.
I have to express my skepticism at this whole thing.
Okay.
I've seen many pieces of work pretty much trying to do the same sort of thing. And they all don't work out because I actually don't even know how you're going to make any of this actually happen in reality. So what does it mean to have Wi-Fi and so on? People have looked at this problem from sort of bandwidth sharing perspective as opposed to, 10 years ago or 8 years ago, we had this new mesh networks and we thought, well, everybody has a DSL connection, let's try to use their DSL connection and use the mesh backbone to do this. And every time everybody has gone down this path, and multiple people have, they sort of build these mechanisms, but they just don't go anywhere. And so in some sense, when I listen to your talk, I actually would like to see what you think about that aspect as well, than just the mechanism itself, right? Do you understand what I'm saying? So I have issue with.
Well, so one thing I can say to this end is that we have implemented this, and we have.
What does it mean to have implemented it?
So we've implemented the forwarding mechanisms and the auction mechanisms.
In what scenario? What is the scenario?
So our evaluation test bed was laptops with EVDO cards. So from Verizon, Sprint, and yeah.
So you're saying that there are multiple laptops here, and everybody has EVDO cards, and you're sort of using that to pull it down.
That's right.
Okay. I don't want to derail your talk.
Okay. So I just want to give a very high-level overview of the various components of Hoodnets, and then I'm going to jump into a couple more details, time permitting. The first is that we do not have control over both ends, and so we introduce this notion of these proxies. So recall that multiple senders, multiple neighbors, multiple Hoodnet peers could be forwarding my traffic, even on a connection-by-connection basis. And so we're going to need a way to, something to act essentially as a NAT. And that's one of the things that proxies do. They do some other things as well, which I'll mention briefly. The first thing is how do we forward to these NATs? And we use what's called two-proxy routing. So for a given packet, if I forward to one of my peers, he sends to his own proxy, and that proxy forwards to mine. Now, I won't go into too much detail on that, but one of the things that helps out with is in terms of the accounting that's necessary for the various auction mechanisms we're going to use. And then the other thing to know is that this logic is mirrored between the proxies and the peers. So while I'll be transmitting like this uplink, they also have various similar kind of forwarding strategies for the downlink. As for how to forward, we have some various forwarding schemes in order to try to gain us high performance. So a few things there. One is we're going to estimate the delay of these highly variable links and try to order the packets such that they will arrive at our proxy in order. But in the case that we fail at that, if they do arrive somewhat out of order, then the proxy has some logic on its side to buffer the packets for a little bit of time and order them before sending them along to the destination. The last major component here is that peers are going to negotiate access to one another's links. So the basic idea is that peers will be paying one another for access, and this access might appear in a form like this. So say you get some amount of bandwidth from me over some period of time. I'll go into what exactly they end up selling. And what's more is because this logic is mirrored at the proxies, all of the auctions are still going to happen on the Wi-Fi network, and we'll send the results back to the proxies. And I'm going to explain a little bit why we need to do that. So in the remainder of this talk, I'm going to just focus on the mechanisms, the auction mechanisms involved in how they negotiate this. So there are a few goals here. The senders are going to be buying, and the relays are going to be selling their links. And what we'd like to do is we'd like them to be able to, as I mentioned, express their valuation, and we want to match their valuations efficiently. So I'm talking in terms of, say, market efficiency. So if there's people who are willing to buy and sell at a particular price, we'd like to match them up. We want to allocate these resources fairly in the extent that the more a buyer is willing to spend, the more that buyer should get. The lower the price the seller is willing to work at, the more work he should get. And also, there's this other interesting component, whereas a lot of auctions in these types of systems, in types of prior systems, have looked at just this notion of how much should I bid. This also takes into account where should I bid, because I have multiple choices on a packet-by-packet basis. So these are some of the metrics we use for evaluating how good one of these negotiation strategies is. We'd like to have high link utilization. If people are willing to spend money and willing to share their link, we'd like to make use of it. Also, in terms of one of these nice sort of policies in terms of how to price our packets, I like the ability to fast-track certain packets. If I could, say, up the bid of some of the packets early in a connection, establishing the connection, opening the window, that'd be really great. And also, we want to ensure low jitter. And so in terms of that first property, high link utilization, one of the first things that comes to mind, which has been explored in previous literature, is this notion of a per-packet auction. So this ability to put bids in a packet-by-packet basis to move that along. So we do that as well. So here's a seller. He has his reserve price. Each packet that he receives is going to contain a bid. He verifies that it meets the reserve price and then enqueues it. The highest bid that's enqueued wins. Every time this peer has the ability to send a packet, he dequeues the highest bid in that queue and sends that. So what that means is that as packets come in, he's going to sort them in terms of the order of their bids, and at last, choose the highest bid to win. Now, of course, there's this notion of, well, how much should that peer be charged? And what we employ is something very similar to a Vickery second price auction. So rather than paying my highest bid, I'm going to pay the second highest bid. But notice that this is a little bit different from a standard Vickery auction, that I could have multiple bids in this auction. So the green peer, for example, has not only the first place bid, but the second place bid. And so one of the concerns here is that it might not uphold the properties of the Vickery auction, because the key property to get truthfulness from the second price auction is that what I pay, if I'm the winner, is not dependent on what I bid. It's whether I win is, but not what I pay. But if we just took the second price here, it would be dependent on what I bid. And so instead, we charge the highest bidder the highest bid that was not his. So in this case, that peer would be charged 4, and his packet would be sent. Yes?
From what like search ads use?
What, who, I'm sorry?
Like Google or Bing, for ad impressions, they're running auctions behind the scenes.
So my understanding is that they do use something like a kth price auction. So it's somewhat similar in terms of this notion of, so the second price auction is used in a very, very broad class of domains.
Is your setting any different in terms of just the properties of the auction that you're running? Is it any different from the search ads auctions that get run?
I'm not sure. I don't know all of the various components that go into that. I imagine that they have other types of preferences they can specify in their bids. So I'm at a very high level, second price auction, very similar, but I don't want to speculate as to what other considerations they're allowed to put in their bids. So putting on the theory hat for a moment, there's some nice properties that this kind of auction has. First off, we get truthful reporting because we're effectively employing the second price auction. Also, it's fair. somebody who bids more is going to get more access to the link, and somebody who has a lower reserve price could get more work, for example, because less of their packets will be rejected. And also, we also have this market efficiency. There's high utilization of the links. At any point in time, I can always pay money and make use of someone else's link. And at the same time, nobody has to do more work or pay more money than they desire. One of the technical issues, putting on the technical hat now, because we want to build these systems and put them to use, is this notion of starvation. So imagine I have some packets enqueued at the sender, but then high-valued flow starts coming in and bumping my packets out again and again. The issue here is, of course, that my packets might be delayed indefinitely. They might live at someone else's queue, and I want to make progress with this connection. So there's a couple things we do to mitigate this starvation. The first is that every packet contains not only a bid, but also an expiry time. And peers may resubmit their bids in the event that their packets can't get out. So for example, suppose that the sender sees that one of my packets has expired, and so he drops that packet. He informs me that that's happened, so that then I could find another peer who perhaps has a higher reserve price. It's not exactly the ideal peer to send to, but at least I know I can resubmit that bid somewhere else in an attempt to get it out there. So I want to present very quickly one of the results from this. And this is from a simulation. It's kind of a toy scenario in that it's not TCP aware, but we are going to look at how packets arrive out of order. Because one known result, of course, is that if packets do arrive out of order, then that can drastically hurt TCP performance. So on the y-axis here, we have frequency, and on the x-axis is how out of sequence various packets have arrived. So how far out of the sequence that they would have otherwise. So the ideal here would be just a straight line right at 0. Everything arrived in order. But in practice, these per packet auctions can incur vast reordering. Now these two modes on the sides are the instances where the packet was bid in one place, expired, and had to be rebid somewhere else. So this is very bad. And it has some nice properties, the per packet auction, high link utilization, fast track packets. We can always increase the bid. But we have this very bad jitter. And so this brings up this notion of, well, what about a different mechanism? Suppose that instead of bidding packet by packet, I actually purchased some promise, some long-term access to your link. And so for that, I'm going to introduce this other primitive, which is what we call a bandwidth lease. The idea behind a bandwidth lease is that I'm going to be able to actually purchase a promise from one of my peers for bandwidth over time. For example, I get 50 kilobits per second from you over the next 10 seconds. And in practice, this is going to be realized as waits and queues in weighted fair queuing scheme at the relay. And so to be able to negotiate this kind of promise, yeah?
These are mobile phones you're talking about, right? Yeah. What if I make such a promise and then just go away?
You can't. So you won't be compensated for it if you do that. That would be the outcome of that. But you're exactly right. It could go away at any time. Your battery could go away, certainly. So to be able to negotiate these kinds of promises, we're going to use what's called a spot market. A spot market is where we have multiple buyers, multiple sellers who all meet at the same time, and we want to fairly allocate the market. So allocate the buyers to the sellers in a way that is efficient. We allocate as much as possible and fair. One of the interesting things about these spot markets is that you have to run them at fixed intervals because you want everybody involved in the spot market at the same time. It'll increase competition and it will ensure market fairness. It helps insist in that. A very common approach here, and you bring up this notion of running these mobile phones, is that they're computationally bounded. So a very common approach typically is to apply what's called a combinatorial auction. But these are, in general, NP hard. They can have very, very large bids in terms of what all the information you need to express these bids. So while they have nice properties, we're not going to go with that. We're going to go instead with a much simpler spot market. And so here's the brief run through. So this is a kind of a spot market that is applied in other economic settings. On the left side, we have buyers. On the right side, we have sellers. Peers value slices of bandwidth. This is how many slices of bandwidth they want, these quanta. So for example, 50 kilobits per second. And they also express how much they value each of these. So this peer wants 200 kilobits per second for each increment of 50. He's willing to spend $1.50. So we're going to assume that everybody knows everybody's valuation, so they're somehow expressing this. And then locally, everybody runs the following algorithm. The first step in this, so the goal in this is to match high bids to low reserve prices. The most ideal bidders, the high bidders, with the most ideal sellers, low reserve prices. So the way we do that is we sort the sellers in terms of decreasing order of their bids, so $2.50, $1.50, $1, and we sort the sellers in increasing order of their reserve prices. And then we start matching them up. So this peer B gets both of the quanta that X is offering, and he also gets 4 from Z. So that meets X's demands in terms of what he was willing to sell, meets B's demands, meets Z. A gets 2 units from Z, but as we try to keep matching them up more and more, we see that we have to stop because A is only willing to spend $1.50, but Y isn't willing to forward for anything less than $2. So we know at this point we can't match up anymore. The bids aren't going to get any bigger, and the reserve prices aren't going to get any smaller. So what that means is C and Y aren't going to get any allocation here. C's not going to be able to buy, Y's not going to be able to sell. Yeah.
What's the notion of rendezvous for these markets? I mean, is that something that you're punting on, or like how does that work?
Rendezvous, I'm sorry?
Well, so we all show up on the bus, right? We've all got our mobile, USB dongles or whatever. Is there a spot market beacon that I somehow listen for, and then, I mean, like, because it seems like this could be a non-trivial problem, actually, getting everybody to figure out, oh yeah, okay, this is the spot auction I should be on, and now here's who I should be talking to.
Effectively, so these are happening every 10 seconds or so. Okay. And so what effectively happens is somebody mentions it. Somebody mentions, hey, here's my bid, and then or waits for some period of time, sees that nobody else has mentioned it. Somebody mentions it, and then they all sort of start jumping in. So we can't match up anymore beyond this. The other notion of the spot market is that we're going to have a single price that all buyers are charged. So what could that clearing price be? Well, actually, it could be anything between the lowest winning bid and the highest winning reserve price. So notice why that's the case. It could be anywhere between there. Everybody above that line is happy with that. The buyers, they were all willing to spend at least $1.50 for that, so that's certainly not a problem. And the sellers were all willing to sell for, nobody was asking for more than $1.25, so they're happy with that. And what's more, there's no sense of envy for those below the line. C wasn't willing to enter that range, neither was Y. So the standard approach here is to just split the difference between the two, so it'd be $1.37.5. Yes?
In there. Like, it seems it's not a unidimensional market in the sense like there's bandwidth and quality of service as well. Do you take that into account? Like, you may be willing to offer me a lot of bandwidth, but at very high latency versus somebody offering low bandwidth but low latency.
Sure.
And it seems when you're talking about cellular backhauls and things like that, those actually may end up dominating. And so it's not, I mean, the problem seems a little bit more complicated here.
So we were mainly going for high throughput, high bandwidth links, or high bandwidth connections. We've looked a little bit in terms of expressing latency, but I would like to discuss that some more offline with you. But we haven't looked at that much more. So this is predominantly just looking at improving bandwidth performance. Yeah.
To some extent, your bandwidth is going to also depend upon not just the cellular link, but where you're going, right? I mean, the whole backhaul. How is the client even going to know what bandwidth they can offer? I mean,
so the basic idea is that because these are happening at these 10-second intervals, that some measure of what my bandwidth is now is a reasonable indication of what it will be over the next 10 seconds. So they are happening relatively quickly.
No. What if well, this is unlikely, but what if the bottleneck is somewhere else and not on the cellular network?
Then you're right. I wouldn't know how to predict that. It would just have to be. I'm assuming that based on how I measure it in one round will be a reasonable prediction for what will be the following round.
Just to follow up on Rathan's, you can have your prices specified based on the quality of the link, right? There can be a correlation between the prices.
Sure. It's a matter of how you match up the bids. So for example, at what point am I willing to give up latency for bandwidth? And so that it's in terms of the valuation expression that is unclear to me at this point. So some theoretical properties of this is that it's fair, it's efficient. I'm going to start moving much more quickly at this point, and that it's computationally inexpensive. So on the one hand, we don't get the truthfulness that we have in Vickrey auction or that combinatorial auctions get us, but we do have computational feasibility. One of the practical issues is bid manipulation, which I'm going to try to go through quickly, which is that I could wait to see what other people say to manipulate my bid and change the reserve or the market clearing price. So what we do is we exploit the property that they're broadcasting over this wireless medium, and we have a two-stage protocol where first I commit to my bid by transmitting the hash of that bid, and only after the fact do I actually reveal that bid. So if I do try to manipulate it, then you'll be able to see that I did manipulate that bid. And again, for some of the details for the remainder of the talk, I'll be happy to discuss them offline. So where this was the case with the per packet bids in terms of reordering, we get much closer to that ideal with this because I have this notion of I know what I have access to at my neighbors. So we have the converse here. We don't have this high utilization because I have to wait until the next market period, as James is bringing up, until I can purchase access. I can't fast track my packets because once I have access, they just kind of go through. But I did get load jitter. So how can we resolve this? Neither of these mechanisms alone is enough, but actually it turns out you can combine them quite well. So quick walkthrough on how do we combine them. Suppose x-axis is time, y-axis is my send rate, and this purple line is my link capacity. And these are the various times in which the spot market is being held. Then here's what happens. As I start sending and I reach my link capacity, I can start bidding in per packet auctions, purchase enough capacity to get me to the next epoch, the next spot market, at which time I can purchase leases, which would increase my available capacity. And as that continues on, I can go ahead and buy some more with the per packet auction. So the idea here is that if I know my demand, I'm going to bid in these lease auctions. And if I don't, I can always bid in the per packet auctions to be able to meet whatever my demand ends up being. So as we combine them, we see that we actually maintain very nicely, like near this ideal in terms of packet reordering, because we're only going to reorder in those times when we've exceeded our capacity and didn't have a chance to buy a lease yet. So they combine very well and can meet a wide range of demands as a result. So to summarize, we've implemented this, we've evaluated this. I just want to give a quick, summary of the other results. I won't have time to go into them. We've implemented them, as I mentioned, on Verizon and Sprint EVDO cards. The ideal would be to get perfect sum aggregate throughput, and in practice what we end up getting is about 85% of that, and that's without going too far down the road of trying to optimize that. And also we're working at the user level using the ton driver. So it works, and it's good for users. They can get improved performance and express this negotiation. Is it good for providers? So I just want to briefly mention that, so these are coverage maps from Verizon, but the data was supposedly gathered from others, so take that as you will. One of the things that Hoodnets would potentially help providers with is with offering broader coverage. Right now, if you're in a place where there was a nearby, say, AT&T user and you're using Verizon, you can't access the AT&T network because of the heterogeneity of the devices. However, with something like Hoodnets, if they both had a Wi-Fi link, then Wi-Fi could be the lingua franca of that, and they could submit their packets to one another and achieve load balancing. So it creates this possibility for other future business relationships between these providers. What those business relationships would be isn't necessarily clear, but it seems to me like it does open up the possibility for provider deployment. So quickly summarize Hoodnets. It bonds selfish links. It addresses both the practical and theoretical concerns. The practical concerns of applying these theoretical mechanisms. So for example, the starvation I mentioned, the bid manipulation in spot markets, and that we have these general mechanisms that could apply in a broader sense. So one example would be, for example, cloud computing, where if I know, say I have an elephant, I know this is going to be an elephant, then I could bid in something like a spot market for these leases, and then if I have a smaller, one of these mice, I could bid in the per packet. So to summarize the overall work that I presented here, cooperation in the internet can no longer be assumed. I presented some theoretical constructs and some ways to apply these theoretical constructs in order to achieve better performance and to achieve better resilience to selfish attack in a wide range of systems. And also, by building and evaluating these mechanisms, we can also develop ones that generalize, as I just mentioned. So in addition to these two pieces of work, I've done some work from a broad set of various areas covering wireless, designs of future internet, also largely here during my two internships, looking at these problems of security and privacy. But I want to end with this notion of what's coming in the future. So this question that's been coming to mind lately has been, how would you define the internet? So originally, as I mentioned, it used to be this interconnection of computers, which the goal was simply to try to communicate. But now, there's many things that are intrinsic parts of the internet that you would be hard-pressed to not include in the definition. Advertising, for example. Is that a part of the internet? It sure seems like it's something that's not going away. Users now are sharing this personal information. There are competing services. There's this expectation of ubiquitous availability of the internet. So our very definition of what the internet is, I think, has changed. My vision is to design systems that address the competing interests of this new definition of the internet in a way that addresses the needs of the users while also recognizing and appealing to the desires of the service providers. And I think that to provide good properties for users, we have to do this, and we actually have to take the pricing model of the internet into account. By pricing model, I don't mean the specific amount that's charged, but by taking into account who pays whom and for what work do they pay, and trying to ensure that whatever work they are getting paid for is good for the users as a whole. And here are just a couple examples of some areas of work that I'd like to look into, and I welcome talking about this some more offline, and I welcome your questions now. Thank you very much.
Got about 2 minutes for questions.
Yeah.
So I actually think that the internet has a beautiful design. It's amazing. So it didn't anticipate personalized advertising, and
Sure.
it came and it accommodated it. So I'm not, and it's also got this layering notion.
Absolutely.
So I don't really know what this means. We have advertising, it's nice, it's beautiful design already, and not quite grokking this vision.
So it's the vision is that I believe it is a beautiful design in the sense that we've been able to do so much. And what I want to do, I think, could also be done on today's internet. The problem is that we do have these services, we have these things up top, but they come at hidden and sometimes not so hidden costs. For example, personalized advertising, there's these competing interests. On the one hand, service providers such as Facebook has every incentive to try to get as much user information as possible to more personally target the ad. But then there's this hidden cost to the user that now there's this loss of privacy. And so can we meet the needs of the users, protecting their privacy, or at least allowing them the ability to remain private, while addressing the desires of the service providers, like Facebook and these various service providers, to, as for this example, try to benefit from the revenue of ads. And that's one example that I've been working with JD, Jay, James, and Thomas. That's what I did last summer. Any other questions? All right.
What you said is not really that there's something wrong with the internet, but it's you want to augment the...
Oh, absolutely.
Like there's something wrong with privacy that Facebook is doing.
Right, so that's not the internet's fault.
But that's sort of the question: is what this broader question of what do you consider the internet to be? Is it just the 7 layers? Is it just the internet connection of computers? Or is it also these other services as well? And I think that as we design the systems, that's sort of the point I'm getting at, is that these systems, what would seem lower level, that would seem to not need to incorporate these things, I think do need to take these higher level competing interests and considerations into account to get the good properties for the users.
Thank you, Spiegel, again.
Thanks.